Hello, and thank you guys all for taking the time to come out and listen to our presentation. We are Pipette Team 10, also known as The Block, and we are here to present to you our automated micropipetter. So here's a little overview of what we're going to be talking about today, as well as a rendered image of our micropipetter. So let's go ahead and meet the team. My name is Buck Daly, and I'm here with my teammates Everett Christian, Ryan Overholt, Carlos Bello, and Jonathan Holy. And we are all senior mechanical engineering students here at UF. We've provided our emails, so feel free to reach out if you have any questions or comments. So now we're going to talk about our hedgehog concept and what makes our design different than all the other designs that are currently available right now. And that is our design focused on three main things: simplicity, strength, and precision. For simplicity, we were able to design our pipetter to only use one motor, the NEMA 17 stepper motor, to carry out all the functions necessary, including liquid aspiration and dispensing, as well as the ejection of disposable pipette tips. Not introducing a second motor made it easier for wiring and assembly, as well as keeping the cost to a minimum. For strength, our design utilized an SLA printer that used Formlabs white resin. Printing on an SLA printer not only allowed us to design with smaller tolerances, but it gave our pipetter more strength and durability. Additionally, SLA printers consistently produce parts with higher resolution and are much more reliable than FDM printers. No offense. For precision, our pipetter used a piston. For precision, our pipetter used a piston that has two nitrile rubber or NBR O-rings. The two O-rings were selected to create a vacuum-tight seal within a reamed aluminum cylinder. This ensured that there was no leaking from the pipette tip that could risk possible cross-contamination. So focusing on these three characteristics gave us a functional, iterative design that was capable of automated liquid handling and tip ejection. Now we're going to dive a little bit deeper and look at an overview of the product itself. So here's a nice little design layout schematic. As you can see, the parts that we bought off the shelf are the NEMA 17, the limit switch, two NBR O-rings, 4 compression springs, and 4 aluminum dowel rods. The volume cylinder was machined out of aluminum, and the rest of our parts were printed on a Form 3 SLA printer. Finally, the disposable tips were provided to us.
So now to move into the product overview and the customer needs that were provided to us. During the design and the development phase of our system, the customer needs were always the main benchmark that we tried to follow. Our main goal was to create an efficient, durable, and precise product that met all of these requirements. Here we go over some of the main requirements that are provided from the customer to us. First being the parameters of size. So 63 by 114 by 236 millimeters were our dimensioning limits. Create a tip ejection system that would prevent cross-contamination while the use of our system. Create a volume dispensing system that would dispense between 500 to 5,000 microliters that had a precision of 10 microliters, and then to keep the total mass under 5 kilograms. Going on to this next slide, we provide a more in-depth approach on how we were able to keep these needs and meet all of them. So the first requirement, we were able to keep our sizes to 62 by 100 by 228 millimeters, which were all within the parameter limits. For the second requirement, we developed a durable spring-loaded tip ejector, which, as you can see in this image, was supported by 4 aluminum dual rods that reduced the buckling stress on the subassembly, increasing the endurance basically and reducing the fatigue on that subassembly. And then for the third requirement, we used a dual O-ring piston along with the NEMA 17 stepper motor that allowed us to dispense up to 5,000 microliters of volume with an accuracy of around 3 microliters. And then for our fourth requirement, we were able to keep the total mass of our design below the target amount, since we used a lot of lightweight materials in aluminum and printing most of our design in 3D printing it in resin, keeping the mass at about 0.847 kilograms, which included the mass, which was mostly the mass of the motor.
You're muted.
Buck, you're muted.
Ryan, you're muted.
All right, so moving forward, we're going to go through a more detailed look at each of our sub-assemblies. So starting with our liquid aspiration and dispensing assembly, we developed a linear actuator to utilize the rotation of our NEMA 17 motor. This was done using a drive nut connected to a plunger, translating up or down in accordance with the rotation of our NEMA 17 motor. And here we actually have a little clip of this functioning in real time. You can see us aspirating the liquid and then dispensing it without any drippage. And there we go. And so we actually had to develop our initial guess for the degrees of rotation needed for each volume before we were able to get an accurate estimate. So we first calculated this volume per step, and our motor had a resolution of 1.8 degrees, meaning 200 steps per revolution of our lead screw. With an 8mm lead, we were able to calculate a linear precision of approximately 0.04 millimeters per step of our motor. By multiplying this with the cross-sectional area of the inside of our volume cylinder, we were able to get an initial estimate of 3.1416 microliters of fluid dispensed per step of our motor. Using this value, we were able to get an initial estimate for the degrees of rotation needed at each of our desired volumes. The initial estimates for our minimum and maximum values are 286.4 for 500 degrees for 500 microliters and 2,864.8 degrees for 5,000 microliters. Now, when we plugged these theoretical estimates into our code and actually ran this in real time, we found that these theoretical estimates weren't as accurate as we had anticipated. And we needed to calibrate our system to reach the correct degrees of rotation for each volume. So at our volume of 500 microliters, we did 2 iterations of calibration. And you can see on the graph that in all of these iterations, we were able to reach a precision of plus or minus 2 microliters. So that was a pretty tight range, well within our range of 10 microliters in either direction, which we were pretty proud of. And then we also calibrated our system at our maximum volume of 5,000 microliters. And here we discovered that standard error really propagated as our volume was increased, leading to a precision of about 8 microliters in either direction at our maximum volume of 5,000 microliters. We believe this propagation of error might be attributed to possible creep in the motor. When we were looking online at our library, we were given a lot of the comments on that website. We're talking about possible motor creep in the library. We also might have this might be attributed to leakage in the volume cylinder, since we had to actuate much further for that larger volume. And to determine the degrees of rotation needed for any desired volume within this range, we were able to use interpolation with our corrected minimum and maximum rotation values.
One part of the liquid dispensing subsystem that we feared could be at risk of catastrophic failure was the drive nut adapter. Now, the drive nut adapter is shown on the left. It is the gray part in this cross-sectional view. You can see the lead screw connects to the drive nut, and then the drive nut is threaded to the drive nut adapter, and then the drive nut adapter connects to the plunger. Now, the plunger and the drive nut adapter are all printed as one piece. Now, every time the plunger is set in motion, the plunger must overcome the frictional force of the O-rings and the volume cylinder. Now, this creates a load pushing up against the drive nut adapter on the right. Additionally, the motor has to supply a downward force on the drive nut adapter that is equal to the frictional force to set the plunger in motion. And this is pushing down on the left. This means every time the pipetter is to absorb or dispense liquid, there is going to be a bending moment subjected on this drive nut adapter. And this analysis is guided using the Shigley Mechanical Engineering and Design book. Now, to determine what this bending stress is, we determine the bending moment and several geometric quantities. On the right, you can see the cross section of the drive nut adapter, and we determined the distance to the centroid to be 5 millimeters and calculated the moment of inertia as well. But to calculate the bending moment, we have to determine the frictional force provided by the O-rings that must be overcome by the motor to set the plunger in motion. Now, to determine this frictional force, we did an analysis of the O-ring deflection to insert the O-rings into the volume cylinder. The O-rings we used had an outer diameter of 10.5 millimeters, and the volume cylinder had an inner diameter of 10 millimeters. This led to an O-ring strain calculation of 0.05. Using an elastic modulus of 3 megapascals for NBR, this determined a stress in each O-ring of 0.15 megapascals. Then to determine what this force is that is causing the deflection, we multiplied this stress by the contact area, which is found from the circumference of the compressed O-ring and the height of each O-ring being 2 millimeters. Now, this force that's causing the compression of each O-ring is also the normal force that is supplying the friction. So to take that normal force to calculate the friction, it's scaled by a factor of 2 because there are 2 O-rings, and we used 0.63 as the coefficient of friction to model lubricated rubber on dry aluminum. This led to a determination of a frictional force of 11.86 newtons. And this leads to a bending stress of 1 megapascal. So when considering static failure, we have a factor of safety of 65. And that's using the ultimate tensile stress of Formlab's standard resin being 65 megapascals. However, this failure analysis, we expected to find that static stress would not be a problem, and we were truly concerned with fatigue stress. So to consider fatigue, we did analysis looking at the endurance limit of this part. And to find the endurance limit, first, we found the rotating beam specimen endurance limit using 1/2 of the ultimate tensile strength. And then to get the true endurance limit, as this isn't a lab prepared specimen, we scaled by surface size and load factors. And we found the surface and load factor to be 1 and the size factor to be 0.97, leading to a modified endurance limit of 31.5 megapascals, which is significantly larger than the bending stress that this part is being subjugated to, which guarantees infinite lifetime, which is also shown with the graph on the right that explains the relation between cycle life and fatigue stress. This graph plateaus once the fatigue stress reaches the endurance limit, meaning any stress less than the endurance limit should guarantee an infinite cycle life. Additionally, we recognize that this was a completely reverse stress, meaning that the bending moment was equal in magnitude and opposite in direction, depending on whether the pipetter was absorbing or dispensing liquid. Now, this can be seen by the orange and blue arrow combinations on the free body diagram on the right. When the pipetter is dispensing, the blue arrow system is at play, and when it is absorbing, the orange arrow system is at play. To verify whether this completely reverse stress situation jeopardized the fatigue life of this part, we did Goodman criteria analysis, and this led to the calculation of a fatigue factor of safety of 31.25, proving that this design is more than rigid enough to survive infinite cycles. And in fact, a redesign could be done making the drive nut less thick to optimize that cycle life and also minimize the amount of material used.
So now a little bit more about tip ejection. During the process of designing the tip ejector, we considered two main concepts. The first tip ejection concept used a servo motor and a collared arm to remove the pipette tip. This design was readdressed because it decreased modularity, increased the possibility of mechanical failure, and increased the part count. The servo motor also had weak motor torque and might not be able to remove the tip effectively. So our final concept addressed all of these problems by using the NEMA 17 that is controlling the liquid handling to also control the tip ejection. This was made possible by including a removal collar that was held up by springs and seated below the drive nut assembly. When the drive nut translates far enough, it triggers the removal of the collar, popping the pipette tip off. So on the right, you can see a rendering of that ejection collar. And then here's a video demonstrating the ejection in action. All right, so now on to production factors. The total cost of this automated pipette design was $93.78. The most expensive component was the resin used for 3D printed parts, which were used in every subassembly. The SLA resin printing was chosen because it offers greater strength and precision in comparison to FDM printers. Because each of our subassemblies included one or more 3D printed components, the extra strength and precision offered by the SLA printing was ruled worth the additional cost. The total assembly time was 6 minutes and 43 seconds. The main limiting factors that contributed to this lengthy assembly time were the abundance of fasteners and the use of through bolts. This requires the assembler to secure nuts in awkward, hard to reach locations in order to fasten the bolts properly. This could be mitigated by incorporating threaded inserts for fasteners to eliminate the necessity of using a nut. This improvement would also decrease the part count, increasing modularity. Thank you guys for coming out and listening to this presentation, and let us know if you have any further questions.
Why are you guys ragging on my FDM printers?
You know,
Oh,
SLA
whoa.
printers just have higher resolution and they're stronger. So we deemed it necessary to make the parts out of SLA because we have a SLA printer available to us. Although Prusa's are great. I have nothing wrong.
It
with
was
Prusa.
really also the workflow, being able to have printers where we didn't have to work around everyone in lab, which proved to be very, very nice for us.
What I'm hearing is Matt's off video and muted. Say it sounds like we need to buy more 3D printers.
There's always a reason to buy more 3D printers.
Yeah. So, Rick, did you have any?
Yeah, I've got a couple of questions. So if you could go to your calibration curve slide. So here, I don't know if you did an analysis or not, but on that 5,000 microliter chart, it looks like that lower one on the 2865 might be an outlier that you could eliminate if you did an analysis, and that might tighten up your precision value there, that 7.8.
Absolutely. Sorry, yeah, that was an outlier. We just chose to include it. I don't know why we chose to include it actually, but yeah, that would be a good point. You can see if we cut that off, it's much more tightly spread. But we just kept it there, you know, because we didn't know whether it was human error or if we actually had a range. But after that second iteration, we were able to see that it was almost definitely human error or some sort of extra couple drops we had or something around that.
Yeah, when you're dealing with those small volumes, it's easy to get a misreading, I think.
Mhm.
Then if you could go to your fatigue chart slide. Yeah, this one. So I'm assuming that that slide off to the right is just something you took to kind of show the concept of fatigue. Is that?
Yes, that's correct.
Okay, it's just a little misleading as a result, because it looks like you've got some experimental data plotted there. So just make it clear that that's just for reference only.
Understood. Yeah, that makes a lot of sense. I see how that could.
Yeah, because I was thinking maybe you ran some fatigue testing, and I was going to be somewhat impressed. So,
Yeah, no, that makes a lot of sense. I was just trying to reiterate the relationship between how, like, if you're below the endurance limit, that you have infinite cycle life, but I do see how that could have been quite misleading. So thank you for that suggestion.
Yeah, I actually was going to make the same comment that Rick made on this. And the best way to do it is just to draw your axes and then draw in like a line that would show what the curve would look like with no units on any axis. As soon as you have units on an axis, I think it's real.
Right.
And I was like, maybe they just were wrong and it's not supposed to be kpsi. It's supposed to be like, you know, kilopascals or megapascals or something. But I'm like 140 ultimate KSI is structural steel, like good quality structural steel, not low grade stuff. So
Very high.
yeah, and then the other comment I would make is on your 3D resins, right? You talk about the benefit of going with an SLA resin, but I would suggest a chart in here to kind of show the comparison to other resin types. If you're going to make that choice, right, really get across what the benefit is of that resin compared to another resin. I know you talk to it, but you don't really show how it compares to other resins. At least I don't remember seeing it in the presentation.
Well, you're right. We could have gone a little bit more in a side by side to demonstrate why we chose and why it would be more suitable for our purposes. But yeah, we just touched on it in a couple of different sectors, but we didn't really do a side by side comparison to what was available to us in lab and why we thought going through our resin was the better choice.
Okay, and then the last thing I wanted to touch on is simplicity, strength, and precision. And you talked about simplicity because you went with one NEMA 17 stepper motor instead of two. So I've seen that in a lot of the designs. So I'm curious as to if you could talk a little bit to the considerations of the two versus the one, and why you were originally considering two.
Yeah, so we were originally considering two because we had the tip ejection problem. So we were going to try to mount that motor somewhere in our enclosure, connected to a collar that would push it off. But we found that the motor didn't have enough motor torque or power to actually eject the tip. So we just thought to utilize the motor that was already in there. And then we built an ejection plate around the lead screw. Like the lead screw was in parallel with the piston, and it just worked better. It had the power and the torque necessary to push it off that the servo motor did not.
And it's just a simple addition to increase basically our volume so that to push it off, it was just an extra 200 microliters. It made it a lot easier to just do that than to try to include a whole nother thing, add so many more parts, might have increased the total size of our structure, might have put us over that constraint and maybe the mass constraint as well. So it just was simpler, smoother to just use one motor over the two.
Okay, and then I'm guessing it was just a time thing. Y'all talked a little bit to your fasteners and the fact that going forward you would go with threaded inserts. What was was that more a time thing as to why you had to go with the fasteners you did?
Yeah, absolutely. The time constraint really made it so that we couldn't make the improvements yet, but we know how to make them.
Okay.
One
fair
more
enough.
design iteration would have done a lot of justice towards the assembly time for this design. We were able to really focus on the precision and the functionality. And one more iteration, we would have been able to really fix some of the trickier parts of the assembly that we realized we had.
Yeah, I think it's, always when you have, I always think of the IKEA instructions, right? Whoever makes those instructions, they should have to put the furniture together, right? It's same thing here. You learn a lot from actually assembling what you've designed as to how you would do it differently.
Mhm.
So good job, guys.
Thank you.
Thank you.
Thank you.
Thank you.
I think a lot of teams actually got really lucky when they made a design change. It actually made their life easier with assembly
Mhm.
time. And you guys just happened to roll the dice like right in the middle.
Yeah.
With like some teams are like, oh, we're gonna make this change. All of a sudden they realize, wait, this one change actually we can assemble it in 4.5 minutes now. And you guys just didn't get lucky with how
Mhm.
those first couple of revisions happened.
Yeah.
Right.
So, but anyways, we are right on time. So I'm going to stop recording.
Cool.